when I solved problem 2, I wasn't quite sure what was the definition of the completion. To me, completion is a topological concept. So I wanted the completion of a line to, to be the set of dense points of the line. However, it turned out that I hadn't read the section very thoroughly. So let's just look at that, and then I'll go on from there. So this is from the book we are working on. So they actually define the where's the completion defined? Well, given a homogeneous polynomial, so that's a prerequisite that we have a homogeneous polynomial. And then we look at solutions to this equation, which of course are form an affine curve, and all the solutions to the equation is called the projective completion. So when I read it, as much as I did read it, it made total sense. I didn't think at that time that I would always think of completion in a topological sense. But then I'm not quite happy with it anyway, because if we have an equation then that can of course come from this equation. Oh, we must have set on it. My God, that's very difficult to me, this. But then it might also come from this equation. If we set z equal to unity, it in both cases reduces to the first equation. And here we have all the points a point, b point, 0. So the whole line at infinity is a solution. And here, of course, we only have like 1.2.0 at infinity. So that means, given a line, we don't know which polynomial it actually comes from. So what we have here, it's not well defined, because one must have given the polynomial in advance. However, if we have a polynomial f of x point y, then we can choose f tilde to be the polynomial of least degree that is homogeneous. So in case of algebraic curves, it's okay. But then how about y equals sinus to x? And now let's just work in the projective, the real projective space. We surely believe that the completion contains this point and no other, because the graph is always close to the x-axis. But now the definition of the book fails. So I wanted to check if there was a commonly accepted definition of topology. You see, the one I used when I talked about it was to have a solution on each topology on each affine space. I will just make a new one here. So if we have P2, then we have three affine subspaces where X is unity, where Y and Z. And this is what we consider the normal plane. And they have each their usual topology. To show that, or to accept that the topology of P comes from these, we need to show that an open set which is open in H1 also is in H2. This is pretty clear, but then I thought, couldn't we define it in, and we are working with real numbers now, we say in R3, where we have three-dimensional balls, and then project them to P2. We have to discard the center. And then say that these open balls are mapped into open balls in P2, and that's all the balls that exist. And then I looked in the book I read on complex projective varieties many years ago. I think it was in the late 90s. It's difficult, and it was written without the use of Gröbner bases, so it's more complicated than necessary. I'm sorry about the shadow on the excerpt. So they define the topology as it's inherited by the projection. And then they have to show, of course, that the map to each affine subset is homomorphic, an isomorphy. So we need to show that it's continuous and open. So what's the situation here? I wonder where I am. Yeah. Let's just do it three-dimensionally. 3n plus 1 projected to the projective space. N. And it has the subsets H1 up to Hn plus 1. And then we have to show that when it comes to a ball here, it gives an open subset in each of these affine spaces. And on the other hand, the original set of each open is open in C. And it's pretty trivial, but it's work that has to be done. So with this definition, we should be able to ask, this question should make sense. What is the completion, the projective completion? Is it this point? And it's easy to see that it's dense. because we have the points n pi point 0. They lie in the affine space. And they equal this in the projective space. And they are equal to 1.0.1 divided by n pi. So they are dense at this point. Actually converges and tends to infinity. Now, the next thing is to take a point where B is distinct from naught, and then show that there is a neighborhood around this point that contains no points from this curve. And I haven't prepared this, so now you'll see me working on a problem where I don't know what to do. So if we use the topology with going a certain distance in each direction, it's called the cubic topology, instead of using balls, then we have in that neighborhood, we have, let's just take it as intervals. Oops. Oh yeah. And we have to show that we can choose delta so that none of these contain none of these points lie on this curve. So how could we go about that? We have to go back to the affine coordinates. So that is, we have to divide by this. And since we are in affine space, we must have delta distinct from, the point in here must be distinct from 0. Let's call that Z. So A, beta, Z. So we define by Z. That's the point. So we must show that they can be chosen such that beta divided by Z is larger than 1, which means that beta numeric must be larger than Z. And we can do that by saying we have set numeric is smaller than delta. So if we choose delta to be the half of b numeric, then z is smaller than this, and beta is larger than b numeric plus delta, no, minus delta. Which delta is positive in itself, that was silly, which is equal to half b. So I think that proves that this is this point is the only one in the completion of this curve, and that is in a topological sense. So that was the cause of my confusion, that I hadn't read the definition and I hadn't noticed this problem at all. So this concludes my little addendum to the solution of problem 2.